All right, so let's go in and let's break our program for right now. Because right now our program relies on spaces, right? So if we come in here and we use that exact same input, 127 plus 13 times 4 minus 1, but omit all the spaces, notice that our output is, it's just the original thing because that's what's at the top of the stack. So we really want to break this guy apart on those operators, not dealing with the spaces. But really what we want to do is we want to ignore spaces. We don't want spaces to be part of our operators either. So we're going to use a tool called the string tokenizer. So what I'll do here inside of shunting yard, the fill input queue, this guy down here. So here's where we're doing this whole cur value thing, this stuff. What I'm going to do instead, I'm going to create this thing called a string tokenizer. This is going to be a new string tokenizer. And I'm going to give this guy the string that we're tokenizing, which is going to be this dot input. And then what the delimiters are, we're going to say plus, minus, times, divide, like that. And then we're going to say true. Yes, I want you to give me the delimiters as well. Okay? So what this will do is originally this will tokenize, it'll split it up on anything that's in this list. So either plus, a minus, a times, or divide, but it'll ignore those operators themselves. Since I said true here, I'm saying I also want those delimiters. Give me those delimiters as tokens. So now I'll say while st dot has more tokens, so as long as there's still stuff in that tokenizer, I'm going to say input queue dot add end. I'm going to add a string. And the string I'm going to add is going to be st dot next token dot trim. That'll take any extra spaces off the end. So what the trim function does is, for instance, if you had a string that looked like that, trimming that would give you that. So it trims all the white space before and all the white space at the end. But it would not take space out of the middle. So it would still look like that. Make sense? And trim exists in most programming languages. That's kind of a tool you can pretty much rely on being there, because that's something you might want to do to kind of massage strings that might have an extra extraneous space or something. So when I go ahead and ask my tokenizer to give me the next token, and when you do this, when you say st.nextToken, it removes it from the tokenizer. So when you call it, it's now no longer in that tokenizer. You've removed that element. So if you need it again, store it somewhere. Okay, so I'll store the trimmed version of that guy in my input queue. Now I'm going to go ahead and just comment out all the rest of that. So this is actually all my logic for filling the input queue. Run this again. I'm going to run it using the spaces that we had before. So 127 plus 13 times 4 minus 1. So I'll explain it in more detail here in a second. Let's just make sure that this works. This other one. 127 plus 13 times 4 minus 1 with no spaces, and there's the same thing. All right, so there exists a class called string tokenizer built into the language in java.util. All right, so string tokenizer is an object that takes a string to tokenize a string representation of the potential delimiters and a Boolean that indicates whether you want the delimiters to be returned as tokens. So for instance, if I had the string 127 plus 5, or we'll just use our exact same thing, plus 13 times 4 minus 1, the string tokenizer, if I pass that to the string tokenizer along with the plus, minus, times, divide as the tokens, and true, that I definitely want the operators as well, what this would give me is they'll give me the 127 space, the plus space, the 13 space, the times space, the 4 space, the minus space, and the 1. And because I called trim on each of these, so what happens is these guys get loaded into this, you can think of it like a queue. But when we say next token, it does remove front. It actually removes it from the list of tokens. Okay? So this is what our tokenizer holds, a collection of all those guys. When I say next token on this 127, that guy leaves the tokenizer and it gives me that string. I then called trim on that string, which will take that space out. And that's the guy added to my queue. Make sense? So because I've done it this way, it doesn't matter whether I have spaces in here or I have 20 spaces in here, because I'm doing a trim, and this one will just give me the 127 with no space. This will give me a plus with a space, but since I'm always trimming, any extra spaces I'm getting rid of. So this is a pretty convenient tool for breaking up strings. Now, if I had passed a false here, I would not have gotten this token, or this token, or this token. It would not have returned those as tokens. It was just using those to split them up. Make sense? All right, so that's the string tokenizer. It's a kind of a handy thing, I guess. Okay, so now that we've upgraded this guy to that, I'll leave this other code in here as just an alternative solution. So this guy assumes a single space between each element. Above solution is more universal. All right, so what I'll do is I'll go ahead and I'll check this into GitHub. So we'll import into version control into GitHub. And which homework assignment was this? 3? Okay, so this is homework assignment 537, fall 2017, homework 3. All right, so I'll go ahead and grab this repository, Go into Slack. Go to 537. I assume everybody's on Slack. Chicago. You got to start calling them that. I'm going to find my tire slash one of these nights. All right. So that's our solution we'll put up there. So now let's go back and let's look at our towers of Hanoi and see what needs to be completed there. So here's our towers of Hanoi. All right, I'm just going to run this guy and see where we left off. Okay, so right now we have our kind of our grid is created, right? And we have this ability to pop from a tower, and this puts it into our like our landing zone, temporary landing zone, and then we can. Do I not? Oh, I haven't written it for the other buttons yet, right? So I can take things off and move them around, or whatever, but I can like go back, I can go off and then back on to the same tower, right? So we need to be able to put them onto the other tower. So let's go and review how we did this. Okay, so we created a stack in here. And what's our stack? Our stack is a collection of nodes. We can push a payload onto the top of the stack. So we wrote this basically today, the same type of thing. We can pop, we can peek. All right, that's our stack. Now, we actually wrote this kind of generically because then we came here to tower. And we decided a tower was kind of implemented in terms of a stack, right? So this guy here's a tower, this guy here's a tower, this guy here's a tower. So a tower is going to be implemented like a stack, where the top thing in the stack is actually a disk. So we kind of upgraded our idea of a node to be a disk. So what's a disk? It's this guy. It keeps track of its size, so it knows how big it is numerically. It also keeps track of the view associated with that disk. And then it knows a pointer to the next disk. All right, and then we have some getters for those things. So I can get the size. I can ask a disk, how big are you? Okay. So a tower, when we first create the tower, he's taking in a view group. Okay, so a tower holds on to a view group. And if you remember, so this whole thing, this guy right here is a vertical linear layout that this stuff lives in. So this is a vertical linear layout, this big square rectangle here. Okay? And I have the gravity set to down in that guy. That's why all the stuff's at the bottom. Okay? So this guy has a gravity set to bottom. Now, when I add stuff in here, it gets added like a stack, right? Because it always adds to the top. Actually, no, it didn't. It gets added at the end. So I added index 0. We'll see this in a few minutes. So I added these things at index 0. Let's actually just look at that now. So when I go to my towers of Hanoi, actually I'm doing it inside of main activity right now. Here's on create. I go ahead and I create my 3 disks. So here's a disk of size 1, size 2, size 3, and I associate them with the 3 that I pre-built here. All right, so I pre-built these disks, but what I actually do is I remove them from this view group. That's like the first thing I do. So I go ahead and programmatically grab these guys. That's this right here. So this grabs those guys. I also have a landing zone. So that's my temporary place to put it. And that is this horizontal linear layout up here. That's currently flattened because the height wraps content. And since there's no content in there, it's flat. When I put something in there, then it will squeeze out. So right now there's nothing in there. If I hit this tower, we remove something from this view group and we add it to this view group. And that's why it now looks like something. Okay? So here's programmatic access to our landing zone. Here's programmatic access to my 3 disks. Here's my 3 towers I'm building. So my first tower is built in terms of this find view by ID, r.id, tower 1 layout. So we come back in here. This is my vertical linear layout for my first tower. I gave that guy an ID of tower 1 layout because I want to have access to this container and this container and this container. So right here, I have access to those 3 containers. Those are my 3 towers. And this tower, if we go to the constructor for our tower, a tower is built using a view group. Okay? So we let that tower know about the container that will hold the disks. So I build my 3 towers. Then I go ahead and I push my 3 disks onto my first tower. Now, if we look at the constructor for our tower, notice the very first thing I do when I first create a tower, I remove all the views from that view group. So this was pretty important that I had previously preserved these guys. Right? I have my 3 disks because as soon as I create my first tower here, those 3 disks get removed. If I just comment those 3 lines out, I never push them back on, and we run this, we'll see that that first tower is empty. Because in creating my tower 1, I remove all those views even though I have programmatic access to them. There's nothing in here. Make sense? So effectively, when I created this tower, I took the visual version of my 3 disks out. And then I put them back in right here to set my game up. So when I push them back onto the tower, here's my tower code, here's push. So I take the disk. I say, am I allowed to push it? Well, if the top is null, just put it there. Otherwise, I go ahead and I push it, and this is the visual version of this. So this adds the disk to the underlying stack data structure. This makes our tower look like it has a disk in there. So this is the visual. This is so we'll just do it this way. When I hit tower 1 again, I'm going to push this disk onto this tower. So what will actually happen is under the hood, this disk object, that is the object that is represented by this visual, will get put onto the object that represents this tower. And then the last part there, this part right here, where I set this tower's view at bucket 0 to be the view associated with the disk that I'm pushing. So only the very last step will I actually take this view and add it to bucket 0 of this view. So I visually see the representation of that tower. Make sense? Under the hood, some stuff happened with my the tower data structure, the stack data structure for our tower. Now, what does this guy not do? We could say currently does not check the Tower of Hanoi rules for placing a disk. Right now, we just let it go on there, right? So we're not checking to make sure we don't put larger disks on top of smaller disks. That's part of the logic we need for Towers of Hanoi. Pop. takes something off, and removes that view. So if top is not equal to null, we go ahead and grab the top. If it's not equal to null, we set tops to be the next disk in the list. Then we disconnect the disk to return, setting its next disk to null. And then we visually remove it. Make sense? So we're seeing the same pattern over and over again. We're updating our data structure, and then we're visually updating our screen. MVC, separating your logic from what you see. Okay. So I have 3 tower buttons. So we go back out here. Notice we have tower 1 button, tower 2 button, tower 3 button. So here's tower 1 button pressed right now. Now you could do this a couple different ways. You can create 2 more functions like this for the other 2 buttons, or you could use this view to determine which tower called this function, like we talked about earlier today. So you can decide which route you want to go with that. One's not necessarily better or worse than the other than the fact that the logic in here is going to be pretty identical. Okay? So when tower 1 button is pressed, we have a variable we're keeping track of here called temp. So temp is which bucket is, or which thing is currently on hold, what's in our landing zone. So initially we have nothing in our landing zone. So we ask the question here, if temp is null, then we ask the question, if when I peek at tower 1, because this guy's associated with tower 1, when I peek at tower 1, if it's not empty, if there's something in tower 1, then I go ahead and I pop. So I'll say this dot temp is equal to tower 1 pop. And we saw that for tower, when we pop, we also remove the view. So this will visually remove it from tower 1, as well as physically remove it from tower 1. And then I add it to my landing zone visually. Make sense? So temp is the programmatic version of my landing zone. Landing zone add view is the visual version of my landing zone. So that's what this guy does. But that's only if temp is currently null. If temp is not currently null, that means I must currently have something in my landing zone. And what do I do with it? Well, I should push it, try to push it onto whatever stack, whatever tower I just clicked the button for. So in this case, because I clicked the button for tower 1, I'm going to push it back onto tower 1. So I'll go ahead and remove all the visuals from my landing zone. So visually it's removed from my landing zone. Then I'll physically add this guy to my tower 1 by pushing it in there. If you remember from our tower, push does the data structure stuff, but at the very end, it visually adds it. Okay? And then I set temp equal to null. Temp is my programmatic version of my landing zone. So when temp is null, that means my landing zone should be flat. There's nothing in there. All right, makes sense how this currently works? All right, now did I already have this guy checked into GitHub? So what I'll do here is I'm going to say commit changes. Added some comments to assist. Well, here, before I do this, let's add some more comments. So I'm going to come back in here and let's go to Towers of Hanoi. All right, so when I move something, so that's up in my landing zone, right? Then when I click it on something else, when I go to put it here, so if I click that button, this tower is currently empty, so this is legal, I'll drop it there. So we want to think about what's our logic for adding something to a tower. So let's go back into our code. We'll go into our tower object. We'll go into push. Okay. Push says, let's just make this a multi-line comment. So 1, if the tower is empty, a push is allowed, right? Otherwise, if the disk at the top of the tower is larger than the disk I am trying to push, it is a legal move. If the disk at the top of the tower is smaller than the disk I am trying to push, then it is an illegal move and should not be allowed. So this is the logic you're going to have to check when we try to push something on here. So when we come back to main activity, what's the very first thing I'm doing? I am removing the view visually from my landing zone. Then I'm pushing it here. Right now, I am assuming that this push works, but it might not. If it was an illegal move, it might not work. Make sense? So what might be helpful is in here in tower, I'll give you a hint. Make this guy return true when a move was successfully made and false otherwise. This way you know whether to clear out the landing zone or reset it to what it was before we tried to make this move. Make sense? So right now we are making an assumption, because right off the bat, we're making our landing zone invisible. We visually removed it. Then we assume this guy worked. Then we physically removed it. Well, we only want to do this stuff if this works. But remember, we had this issue last time. We actually have to remove it first so that we're allowed to finish putting it on the push. Because down here, I got something stuck. It's funny. I'm actually trying to place the view, and a view cannot have two parents. So had I not previously removed that view from the landing zone, I would not have been able to add the view to this tower. That's why we have to do this line first. so that we can potentially add our view to the tower. Then we'll try to add our view to the tower. So what are we going to do here? We're going to remove view from landing zone so it can potentially be added to the tower. If the push is successful, set temp to null, indicating the landing zone is empty. Otherwise, put the view back in the landing zone so it is visually there, and don't set temp to null since the move was not a legal move. Make sense? So I'm spelling out the logic that you're going to need for these places. Okay. So what you're going to need to do for your homework is you're going to have to make these other two buttons work so we can move stuff between all the towers. They should all play by the rules. And then finally, your code should detect when tower 3 is complete, when you've won. Make sense? All right. And then what we'll do next time, you don't have to do this for your homework, but we want to keep track of how many moves we made. So if you go back in here, you see that it kept track of the moves I made. So actually, I'll restart this. There's 1 move, 2 moves, 3 moves, 4, 5, 6, and 7. That's the minimum number of moves for that. So next time we'll create what's called a singleton. We haven't done singletons yet, have we? Huh? Not in this class. So next time we'll create a singleton that will allow us to do that counting. Okay? You don't have to worry about for your homework. So for your homework, what you have to make work, and you can watch this at the end of the video, is legal movements of your stuff from point A to point B. If I try to make this move, it should not work. And when I finally get all my elements on that far right tower, it'll maybe, print out you won or something like that. You can put it on the screen if you want, or you can just print it out to somewhere you need to determine that you've actually won. Make sense? All right. So questions about any of that stuff? Anything you want me to clarify in the code before any other notes you want me to add before I push it up there and give that to you as your starting point? What do you mean? You only win if you're in the far right tower. Yeah. So, this is not winning. And this is not winning. So let's go this route. That is also not winning. They all have to be in the far right tower. That's the way you win, is have all of your discs in the far right tower as a result of legal moves. Ideally, they would have gotten there by, in the minimum number of moves, but as long as you get there somehow, right? You just play around with it till it finally gets there. Make sense? The only way you actually win is getting it over here. So your game should let you continue making moves until you finally win. Okay, what else? Anything else you want me to cover or give you hints on? I want you to have the best possible chance at being able to get this thing solved accurately. So it's still missing plenty of code. You're going to have to write some code here. But let's see, you're probably missing a total of, well, this same function a couple more times, or write it in there. So in terms of unique lines, you're probably missing, call it 5 lines there. And then in our towers, for these rules, for push, two or 3 lines there, call it 5 lines. And then checking to see if you have a winner. So probably, all in all, you probably only have maybe 15 lines of code that you have to write. That's very specific, 15 lines of code. And that doesn't consider that if you, that's 15 lines of code that, you know, so this is about 5 lines of code you'll have to add to this guy to make it work. And then you can either duplicate that 3 times for each of your 3 towers, or write it generically using this view to determine which tower called it. So if that's the case, then you'll have to have this, you copy and paste it and modify it slightly. So you might end up with, you know, like 40 or 50 lines of code in the end, but you're only going to have probably 15 unique lines of code for the assignment. Make sense? Does this feel attainable? We're all excited. We feel like we can do this. All right. So I'll go ahead and I'll push this up to, I'll commit my changes. Added some comments to help with the assignment. I'll do a commit and push. Okay, and then we'll come in here. And we are 537. All right, and this is programming assignment number 4. And I'll give you my starting point here. All right, this will be due next Tuesday by 5 p.m. Okay, and I'll put the writing assignment up tomorrow morning sometime. I just to brainstorm that a little bit, but it'll be shorter. So I'm thinking it'll be, whatever it ends up being, I'm thinking it's going to be a roughly maybe a page of written stuff, but a very specific format or something like that. Make sense? So if you're just trying to plan out your week for time, don't wait until Monday to start. Got it? Start earlier, maybe. But it should be a smaller paper. Okay, I will see everybody next Tuesday.